Hello everyone. In this video, we will be discussing about basic concepts of finite element analysis where we'll be focusing on loads, equilibrium conditions and the boundary conditions. So generally when we analyze any problem by using finite element analysis, three things we should be very familiar. That is how to identify the load condition and even how to apply that. Then how to write the proper equilibrium conditions, and before moving to that there is a very important thing is the thing about the boundary conditions. So usually when we talk about the loads, depending upon the type of analysis we are doing, either we can go with the force vector, a temperature vector and even a pressure vector. So combination of all three is also possible. Depending upon that, if it is individually asked, we will be going with only the force vector, and if the domain demanding only the temperature solving problems or analysis, then we will be going with the force as only the temperature. And in case if it is only the pressure related, maybe uniform distributed load or uniform varying load, then we will be fully going with the pressure vector. So there are possibilities like combination of force vector and temperature, force vector, pressure and temperature, temperature and pressure, and pressure and force. All these combinations is available even in our syllabus also it is there. Once you start do the complicated analysis in the for the practical cases, then you can evidence. So then you can experience so how this combination will work out. Then moving to the equilibrium equation for the structural components, it is very clearly defined. That is a global stiffness matrix capital K into the displacement matrix, either Q or U matrix, which is equal to the force. That is what type of force is used, either in the normal point forces, the temperature or the pressure. That force vectors will be writing. Then boundary conditions. Boundary conditions is the thing, but just we need to identify or we need to observe what is the loading condition and which point where it is fixed in which how many degrees of freedom. So all those things sometimes will be given directly, and sometimes we need to understand looking at the conditions. And sometimes when you are finding out the boundary condition, there are possibilities where a movement can be given directly, and even some stresses can be also given directly. Such kind of situations also we have to follow this method, that is a force vector, and the stress we need to equate it to the zero. This is the equilibrium conditions. Next one, how the theory can be developed. So basically two methods are there. First one is the Rayleigh-Ritz method and second one is the Galerkin's method. Both the methods initially it was developed to solve all the 1D problems, but for solving 2D and 3D problems nowadays the matrix method is there, or else even advanced softwares are there. But still for the comparison purpose, even now these days also these traditional methods has been used. Under Rayleigh-Ritz method, total potential energy equation can be considered. So what is this total potential energy equation phase? Usually it is denoted by a symbol pi. So it is the summation of internal energy plus external energy which is acting on that one, that will be equal to the output, the total energy equation. Rayleigh-Ritz method, in the previous video we just discussed like who invented this one and what was the purpose, everything related to the frequency and other things. Next one is the Galerkin methods. We can say it's like a bit advanced compared to the Rayleigh-Ritz method, but here the purpose of this Galerkin method is also same, where we'll be finding out the solutions for the 1D problems. Next, moving to the 1D rod elements. So to understand and solve 2D and 3D problems, we must understand the basics of 1D problems. So maybe some students may feel that why still we need to learn 1D problems, like many problems we have discussed, but still why we need to discuss? Because there are varieties of applications are available. So if you want to know, or if you want to do practically, or even the matrix method also, you should be having a very strong foundations in solving 1D problems. It may be a bars, it may be beams, trusses, or temperature related problems, whatever the things, all the basic understandings of the 1D problems is mandatory. Then only you can able to explore 2D and the 3D problems. Next, analysis of the 1D rod problems can be done using Rayleigh-Ritz method and Galerkin method. As I told you, the major purpose of discovering this Rayleigh-Ritz method and Galerkin method was for analyzing the 1D rod elements. Now also for the comparison purpose we can do that one, but compared to the matrix method, Rallids and Galligan methods is a little complicated, a solution, the solution wise, and even the time it consumes. And to solve finite element analysis problems, some are modified into the potential energy approach and some are modified into the Galligan approach. Now here the 1D rod elements we need to discuss in detail. So considering all these factors, first one is nothing but the loading factor. So the loading consists of three major types. First one is the body force, second one is the traction force, and third one is the point load. So we would have never discussed this body force and the traction force when we discuss the problems in the bars and even in the beams and trusses. But actually speaking, along with the point load, even this body force and traction force was also there. Almost for all the 3D analysis, these three forces, at least two forces combination we have to use, or it can be used. And moving to the next one, body force, traction force, point force, the detailed explanation we will discuss here. Body force, it can be of distributed force acting on every elemental volume of body, that is the self weight of the body. When we solve some problems in the bars, where in some questions it is mentioned like ignore the self weight or consider the self weight. So depending upon the density and even the condition of the problem, the boundary condition of the problem, whether the self weight are to be considered or ignored. Next one is nothing but the traction force. Traction force is basically nothing but a distributed force again, but acting on the surface of the body, that is a fractional resistance. So viscous drag and surface shear. So the applications wherever this frictional resistance is experiencing or the viscous drag is there and the surface shear, even the fluid analysis also completely belongs to the traction force concepts only. And next one is the point load, which is the one almost for all the applications whatever we have discussed, where this point load only we have used. So which can be defined as a force acting on any single point of the element. Remember, when we talk about the point load, always it should be acted only on the nodes. But body forces and traction force, it is not having any such restrictions. It can act on any part of the body, need not be on the nodes. So here what is the condition is, if you are applying a body force, a traction force means before itself that particular boundary or a particular location, as much as possible try to establish the nodes, because the forces can be applied only on the nodes. But in case of the point load, that is not the case. After after the discretization and after defining the geometry only, anyway one or another point, a point load can be applied. So like this only it can be converted. Next, along with this previous like major important factors, few more things are there. That is nothing but element strain energy. So element strain energy, it is the equation we have got we have discussed already in the mechanics of material and even in design of machine elements. So the same equations, so wherever the strain energy is being used, usually this will be used when we calculate this shape function derivation or else the stiffness matrix derivation. The strain energy concept will be using for all the deformed structural components. So what is the equation is, usually strain energy is denoted with U and E for the element. So element strain energy, which is equal to 1 by 2 Q transpose KE, element stiffness matrix, into Q. And for the element stiffness matrix for an 1D rod elements, it is Young's modulus into area divided by length of the element of matrix 1 minus 1 minus 1 1. This derivation was already discussed. Then moving to the load vectors, element body load vector and element traction force vector. Traction force we have not discussed yet. Body force we have discussed. So body force, it is area into length into the body force divided by 2 of matrix 1 and 1. For the traction force, it is traction force into length divided by 2 of vector 1 and 1. So this is a common equations which we already discussed for solving the problems. The only new thing was this traction force, which wasn't discussed when we discussed the problems in the module 2 and module 3 numericals. So have you look on these things. So starting from the loads, boundary boundary conditions equation, developments of the theory, and the 1D odd elements understanding, and the different factors